Instead of error going at noon for a hot Americano, then orbit at 12:10 p.m., and another trip at 12:30 p.m., we could send 5 people at once to order 5 hot Americanos. This would streamline the process and reduce the effort of handling individual orders. Hello everyone, it's Era here. Apple has recently launched the new Mac Studio, which is equipped with the highly advanced M3 Ultra alongside the M4 Max. The specifications supported by the M3 Ultra are incredibly impressive, especially in terms of AI inference capabilities, showcasing Apple's strong and dedicated commitment to this rapidly evolving field. It seems like they were well prepared for this. The CPU has 32 cores and the GPU has 80 cores. It supports up to 512 gigabytes of RAM, which is the memory. The SSD can support up to an incredible 16 terabytes of storage. Furthermore, with Thunderbolt 5, you can link multiple Mac Studios together, allowing for an astonishing data transfer rate of 120 gigabytes per second. When it comes to AI models, this single unit can handle models with up to a mind-blowing 100 billion parameters. Previously, if you wanted to run tasks on a server, you would typically need to connect 10 or 20 graphics cards, or even link up 10 Nvidia H100 GPUs. But now, you can accomplish this with just one device, which is remarkable. To effectively run this AI model on what is commonly referred to as AI hardware, you should follow Apple's approach. Apple has equipped this device with ample memory, but it's not just any memory. It's what we call unified memory. Traditionally, CPUs and GPUs have their own separate memory, but since the introduction of the M series, Apple has integrated this memory management. This means there's no need to shuffle data back and forth between the GPU and CPU. By broadening LPDDR, they've substantially enhanced the memory coverage, making it possible to effortlessly run incredibly large AI models with hundreds of billions of parameters. This is even a key selling point they emphasize. The M1 Ultra was already impressive, but the new M3 Ultra is said to be 16.9 times faster. To grasp this concept, we should delve into how AI models are implemented in hardware. It's not just a matter of black and white distinctions, but rather understanding the intricate relationships involved, which can be quite intriguing to study. So today, I'm going to discuss why Nvidia is pushing forward with Project Digit and how their recent collaborations with SK Hynix and Samsung Electronics are resulting in cutting-edge memory technologies. These advancements are all geared towards AI PCs. So, when we talk about our MacBooks or Windows PCs, it seems that Nvidia is preparing to launch an AI PC. This move appears to be a strategic effort to compete with Apple's latest offerings such as the Mac Mini and the Mac Studio. Moreover, Apple has the potential to emerge as a leading force in edge devices, offering incredibly advanced AI services in the near future. By fully grasping this information, you'll be able to understand the direction in which AI trends are heading. Let's delve into this topic for a more comprehensive understanding. First, as I mentioned earlier, Apple has released the Mac Studio. It has a maximum capacity of 512 gigabytes, which is very important. For instance, I can tell you the exact amount of VRAM in your gaming graphics card, or how many H100 or H200 units are used in servers. Of course, the types of these components differ slightly. Even though LPDDR and HBM have their differences, Apple still stands out with its powerful capabilities. Now let's talk about Thunderbolt 5. This aspect is crucial as well. In simple terms, what exactly do NVIDIA's NVLink or NVS switch accomplish? Ultimately, what is the reason for needing multiple GPUs? It's because a single GPU isn't sufficient to process one AI model efficiently. So they need to communicate quickly overall. To do this properly, they acquired Mellanox and implemented NVLink, NVSwitch, and InfiniBand. This enables extremely fast communication. For users, equipping this Mac Studio with Thunderbolt 5 is also significant. It can fulfill such roles effectively. When you look at this, even NVIDIA's Project Digit has been designed to be extremely compact, roughly the size of this Mac Studio. It seems that they are quite aware of this trend. Models such as the V3 or the R1, which are often referred to as mixtures of experts, encompass a truly staggering range of approximately 600 billion to 700 billion parameters. These parameters can indeed be processed in a single operation, especially when they are expressed in a more lightweight format, such as an 8-bit representation. People are exploring this option. With DeepSeek being an open model, they are experimenting with it. To harness this immense capability, for instance, through AWS cloud services, using cloud services and DeepSeek on a large scale has presented challenges. It hasn't been easy to manage with traditional AI PCs. We need to understand why this can be done with just one of these, and why it doesn't work the same way with NVIDIA. What are NVIDIA's strengths and weaknesses here? There have been many attempts like this before. For example, you might have heard of the Mac Mini. Do you see the Mac Mini here? In this particular setup, we are connecting 4 Mac Minis together, which allows us to load AI models along with all their parameters, making it quite efficient for certain tasks. Thunderbolt 4 allows fast communication, though not at server levels. Some want to use it at home for research, like running Llama models. Many have shared their experiences doing this. They often connect it to devices like the Mac Studio. You know these cables are expensive, right? You all are well aware of the Thunderbolt summary I put together. By integrating all of these at incredibly fast speeds and utilizing Thunderbolt 4 to share computing power and memory resources, there's a significant demand for such configurations. There's a notable need for running large model servers on custom-built hardware, and several projects like those by Exolab have involved connecting multiple units together. So, Exolab researchers connected multiple units in front of a Christmas tree. They displayed the generated networking states to show everything is working correctly and swiftly. So this means that the previous models were connected, not the newly released M3 Ultra. This time, however, we're talking about handling an enormous model like DeepSeek, which would require a substantial memory, such as the 512 gigabytes found in the M1 Ultra. This allows you to manage such a massive model effectively. To give you an idea of the scale, both DeepSeek R1 and V3 come with a staggering 671 billion parameters. It has an astounding 671 billion parameters, which is truly remarkable. Now let's assume that we use 8 bits for each parameter, meaning we need 8 bits to represent a single number. Even if we use just 1 byte per parameter, how much memory would be required in total? You need 671 gigabytes right now. One Nvidia H200 has 141 gigabytes of HBM. Using 8 of these GPUs with 141 gigabytes each gives you roughly 900 gigabytes. But why isn't it 670 gigabytes instead of 900 gigabytes? Typically, you use about 1.4 times this amount. We need to store caches and intermediate values during computations, not just increase parameters. To achieve this, we use more resources, but we do not just increase the parameters. Is it okay to have 2? No. Is it okay to have 3? No. You need 4 to handle 671 gigabytes with 8-bit standards. A smaller model with 71 billion parameters can be compared to the Nvidia RTX 4090, you know? The 50 series has just been released, but the 40 series was previously the highest-end gaming graphics card. Although the previous one used HBM, this one uses GDDR. Graphics GDDR. Even though it has good bandwidth, due to the capacity limit, it is said that at least 8 are needed. From a 16-bit perspective, managing tasks with a single unit is quite challenging. But if you look at this table I've compiled, you'll notice that Nvidia is the most familiar. While the Black series is just starting to emerge, the H100 has been widely adopted previously. We have analyzed the memory capacities and the cost per gigabyte for Nvidia's H100, AMD's MI300X, and Apple's newly released M3 Ultra and M2 Ultra. The Nvidia H100 offers 80 gigabytes of storage per unit. AMD and the M2 Ultra have 192 gigabytes capacity. This was AMD's initial push. Because it is equipped with a significantly larger amount of HBM, it has been advertised as providing a much broader memory space that can be covered with just a single unit. But the M3 Ultra suddenly has 512 gigabytes, yet the price is reversed. The most expensive is the H100. We're not sure how it will be sold yet. The estimated price is about $25,000 or 40 million won. Yet, with significantly fewer resources than usual, where typically several units are required to run a large AI model, this new system can manage it with just one unit. When considering the cost per gigabyte, this one is only $20, whereas the other one is $313. This is because the former uses HBM, which is significantly cheaper compared to LPDDR. Therefore, we need to address that Nvidia's performance metrics might appear superior. So you cannot simply say this one is always better, or that one is always worse. What I am trying to explain is that when you are trying to load a massive AI model, if the memory capacity of a single unit is limited, then AI models requiring more capacity cannot be supported by just one unit. However, since Apple supports up to 512 gigabytes, smaller models like FP4 or other 4-bit models can scale up to 600 billion parameters. Thank you. When we use AI, how do we do it? For instance, in an Nvidia GPU, there is the GPU part and the memory part, right? You have HBM and DRAM. Now think about the concept of running this AI model for the first time. When we input something into ChatGPT, what actually happens when it tries to run the AI model? This is what we need to understand. So for the first AI model, we have these numbers called parameters. All those numbers need to be loaded into this memory. For example, If we have 60 billion parameters, they all need to fit into this memory. When we talk about loading parameters, we mean that the parameters of this model need to be stored somewhere initially, so that the AI model has the necessary data to perform its calculations. However, considering something like DeepSeek, which has an immense 670 billion parameters, can it all fit in at once? The H100 isn't capable of this, but the M3 Ultra can manage if each parameter is encoded with 4 bits. The initial step is to load the parameters here, followed by using interposers and indicators for computation. Once the calculations are performed, we can input tokens into a system like ChatGPT, which will then predict the next word. So the process involves going back and reprocessing the data by feeding it back in and repeating the steps. Once the parameters are loaded, the GPU takes over the computations. The results of these calculations help in selecting the next token. This sampling is repeated by re-entering the data for further processing. At this stage, we hit a bottleneck. But what exactly do we mean by a bottleneck? It needs to keep moving quickly, but just like on a highway where there's a sudden traffic jam, the bottleneck here is the speed at which HBM can send data to the GPU. This is precisely the reason why HBM was developed in the first place, to address the limitations and enhance the overall performance. In the past, DRAM, LPDDR, and GDDR had low data transfer rates, only processing 4 times per second. To improve this, we need to significantly increase the speed. By creating a more efficient pathway, we can send data in parallel. This involves linking cores through an interposer to the GPU, addressing a major bottleneck known as memory bandwidth. The speed of data transfer from memory to the GPU is crucial. That's why HBM is needed. It ensures rapid delivery. This is the first bottleneck. The second one is the GPU's own performance. What's the point of delivering it quickly if the metrics are slow? Even if I send it fast, it will just pile up if the metrics are slow. The metrics need to be fast. That's why they use multi-core transformer engines, tensor cores, and more. Originally, the GPU handled graphics core processing. Now it's used for AI processing in a hybrid way, which is NVIDIA's approach. This approach requires continuous development. That's why new metrics and benchmarks keep emerging. These two factors are crucial. Once the terms are set, the process can be repeated similarly. The primary bottleneck is the memory bottleneck. This poses a significant challenge. To tackle this, what measures were taken to boost the bandwidth? Firstly, they had to resort to using HBM. Additionally, we often talk about GPU performance in terms of teraflops, which also need to be improved. So, the question is, does memory bandwidth become the bottleneck? Or is it the GPU itself that becomes the bottleneck? Different situations can present different challenges. When building servers, memory bottlenecks have always been an issue. That's why HBM is truly necessary even now. While GPUs are incredibly fast, the memory does not deliver data to them quickly enough. The AI model is massive, and for rapid computation, I can process it very quickly. However, the necessary data must be sent to me swiftly, but it is not. It is being sent slowly, regardless of the effort to speed it up. This is commonly referred to as a memory bottleneck. In this section, Apple's methodology is notably different. You might be curious as to why. Let's take another look at Nvidia GPUs. Previously, I discussed just the memory aspect, but now, considering the throughput, essentially the volume of data Nvidia GPUs can process and output per second, Apple's cost per gigabyte is indeed higher. This underscores a key distinction between the two. What does this mean? In this case, it's 3 terabytes per second. Apple is 0.8 terabytes. So, in terms of performance, this itself is slow. Apple has a structure that inherently makes it slower. Power ranges from 200 to 250 watts, but can reach 700 or 1000 watts. AMD also goes up to 1000 watts. Devices with terabyte-level bandwidth use a lot of power. In terms of teraflops, Apple's numbers are just 26 and 43, indicating a much lower computational capacity. Nonetheless, it's crucial to recognize that Apple still maintains a significant position in the market. Have you heard of the term batch size in AI? Batch size can be 1, 10, or even 20. It refers to a group. This concept of batch is something all of us from the old days are familiar with, right? Just like how you can create batch files in MS-DOS to group multiple commands together and execute them all at once. The concept of batching can be understood in a similar manner. For instance, if you go to get a hot Americano at 12 p.m., then go back at 12:10 p.m. to get another one, it makes more sense to batch these requests together. Instead of ordering a hot Americano and waiting for 30 minutes, if 5 people order 5 hot Americanos at the same time, the processing cost can be reduced. Thus, calculating this memory bottleneck is quite straightforward. By assessing the extent of the memory bottleneck, we can determine the current memory bandwidth and the number of parameters it is outputting. as well as its potential output capacity. Moving on to GPU computations, it's crucial to examine how many parameters are processed per second. How do we evaluate the parameters processed each second? How many calculations are done per parameter? How many calculations can the GPU do per second? Dividing these gives you the parameter per second. This shows how many parameters can be calculated per second. How many parameters can be processed and computed per second? Depending on which aspect is prioritized, the situation can fluctuate. Therefore, it's often discussed that memory is frequently insufficient. Even if you send data quickly, it won't work due to lack of capacity. Most server metrics show a memory bottleneck. It can't output fast enough. Why is that? Look at this part. You're not familiar with flops per parameter, right? When we discuss the process of training or inferring a single parameter, we're talking about the number of flops operations involved. This is where the term batch size comes into play. The batch size essentially refers to the number of data samples processed simultaneously during AI model inference. This parallel processing is key for efficiency. The reason I'm sharing this is because, when we talk about memory and GPUs, the term batch size refers to the number of data samples that are processed simultaneously as input to the model at one time. Whether it's for training or inference, the size of the batch that the model processes at once is called the batch size. Now, when training a model using an Nvidia GPU, organizing the data into multiple batches enables rapid parallel processing, enhancing computational efficiency. However, if the batch size is very small, let's say it's just 1, then the memory load is significantly reduced. With a batch size of 1, parameters change with each training step. This is in the context of training. Now, what we just discussed pertains to Apple's inference scenario, and this is where the M3 Ultra excels. When discussing the M3 Ultra's inference capabilities, it's evident that it's tailored for a batch size of 1, as it handles a single batch without multiple queries. So just increase it a bit, process it, calculate, and output it quickly. Apple is prioritizing this area, and it's important to take into account the refresh rate since dynamic RAM, including HBM and LPDDR, falls under DRAM. Since it's all DRAM, it needs to be refreshed periodically because DRAM constantly loses charge and requires regular refreshing. Nvidia refreshes 37 times per second. Apple only does it 1.56 times per second. That's quite low, isn't it? The lower this is, the better. Every time the memory refreshes, it takes time, right? When it comes time to transfer actual data, the occurrence of refresh cycles inevitably results in latency. Nvidia GPUs are designed to handle numerous batch sizes simultaneously, ensuring continuous operation for maximum computational efficiency. This, however, necessitates frequent refresh cycles, which inherently cause latency. On the other hand, Apple, it is designed specifically for scenarios with a batch size of 1, where only a single task needs to be handled. This specialization allows for rapid data retrieval from memory with minimal refresh cycles, ensuring quick responses when prompted. This indicates that it is likely optimized for edge devices requiring immediate reactions. In other words, they can dominate the AI PC market by utilizing the Apple ecosystem. It seems this approach is being adopted, especially with the mixture of experts in DeepSeek. Originally applied in Gemini, I mentioned earlier that DeepSeek has 671 billion parameters. That's a huge number, but it doesn't call all of them every time. What does that mean? Of course, the entire model needs to be loaded. The entire model is indeed loaded into memory, but there's a distinction between having it loaded and actually utilizing it for computations. In this regard, Apple's latest M3 Ultra is optimized with the mixture of experts approach. Experts blend their specialties. For a math problem, just run the math model. When writing, you just need the writing base. When coding, you only need to code. These small models can run tasks. But originally, you had to load everything at once, which required a lot of memory. From the viewpoint of a server, using numerous Nvidia H100 GPUs is quite inefficient. You have to handle intricate memory management and retrieve everything due to its distributed nature. Conversely, the Mac Studio boasts an immense memory capacity. Although its computing power is modest compared to a server, it provides substantial benefits. However, if we consider applications that need to respond immediately and operate with a batch size of 1, focusing on minimizing latency, the Mac Studio is actually better suited for deep learning tasks. This is because it utilizes unified memory, which allows it to access a very large amount of memory with high bandwidth, facilitating efficient GPU access. It involves balancing computing and memory usage. For AI that needs to respond in real time, like conversational AI, it has to answer immediately. This also applies to AR and VR, including devices like the Vision Pro. Or consider various on-device AI tasks, interactive applications, and other areas where Apple excels and sees profit potential. They are expanding these capabilities with the Mac Studio at the center. They continuously increase memory capacity. In response, Nvidia introduced Project Digit, which is the same size as the Mac Studio. Jensen presented a compact device nearly identical in size to the Mac Studio as part of their strategic approach. They are advising business operators to create SoC cameras. Jensen Huang is likely preparing applications that surpass LPDDR with a unified memory strategy. These applications can respond to latency immediately with a batch size of 1. So, to revisit the concept of batch size, typically when training an AI model, a batch refers to a group of data that is processed together at once. For instance, if we set this batch size to 100, so, the calculations per parameter increase by 100 times. What does it mean for this to increase by 100? It means the overall calculation capacity is reduced to 1. The more it processes tasks in parallel, the more its overall computational capacity diminishes. Given the existing memory bottleneck, they typically group data into batches for training. However, Apple's approach is different. They utilize a batch size of 1. With this batch size, the computational capacity of the Mac Studio's GPU doesn't measure up to that of Nvidia's. When comparing teraflops, it's clear that they're not on the same level. Got it! Since that's the case, I'll use it in applications that fit batch size 1 perfectly. That's deep learning, and it involves applications with low latency. To summarize, in the case of Apple, the computational power of their GPUs is lower than that of Nvidia. Because of this lower level, even if you want to perform training, it becomes difficult to bundle multiple batches together for training. Even if you have a large amount of memory and high bandwidth, the computational capacity to fully utilize it is insufficient. This means you cannot effectively increase the batch size. To explain in simpler terms, increasing the batch size during inference involves processing multiple user queries simultaneously, similar to how servers and data centers handle tasks. When it comes to processing, Apple doesn't really need to worry about that. They can simply use the GPU capabilities available on their Mac, local edge devices, or smartphones. By assuming a batch size of 1, they can ensure that the latency isn't slow. There's no need to bundle multiple tasks together. It seems that their design is more focused on inference rather than training. This aligns with Nvidia's Project Digit, likely focusing on continuous training. Today's discussion was quite complex. The lecture went on longer than expected. If you have questions, please leave comments. I'd like to make a follow-up video to address them clearly. As I tried to explain, I realized some aspects are quite complex. In my view, Apple currently has a firm grip on the existing ecosystem. As long as edge devices remain, the AI PC market could revive. This is despite the overall decline in PC demand. By approaching it this way, the potential to create something truly remarkable is high, which makes me ponder whether Apple might make a comeback. To ensure they don't lose their leadership, Nvidia is pushing forward with Project Digit. This viewpoint might help you grasp the situation better, and I've shared some technical details as well. I would love to hear your thoughts. This has been Error.